Ready, set, go. Number 1, 3 to the 5th power. That's 243. If you don't know that off the top of your head, that's okay. Do it like this, write out all 5 and then just start multiplying. 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81. And then 81 times 3 is 243. Number 2, we are multiplying with this giant dot here. We're multiplying r to the 2nd power and r to the 5th power. That is literally this scenario where we have 1, 2, 3, 4, 5, 6, 7 r's because it's r to the 7th power. So if you're like, why did you draw that out? Because that is the visual version of this. Now, what we would rather you do is just look at this and say, hey, we have the same bases and we're multiplying, so we'll add the exponents. So speaking of that, let's turn up the difficulty just a little bit. This is m to the 3rd, there's that base, times 6m to the 5th, there's that base, times negative m to the 4th, there's that base. So if I just focus on the fact that we have those m's, then I can do this. 3 and 5 is 8, plus another 4 is 12. And you might think, well, what about the rest? What about this 6? Well, basically it's 1 times 6 times negative 1, which would be negative 6, right? And again, the reason that I did this here was just to kind of show you this is what this meant, but I would not like to write that many variables sometimes. Like, I don't want to write 12 m's, even if I write them 3, 5, and 4 at a time, right? Number 4, we have negative 9, negative 2, that's 18. We have d to the 3rd, and d, that's d to the 4th. We have e to the 3rd, e squared, that's e to the 5th. And we're done. Number 5. So just like this, an exponent means, hey, this is our base, and we're gonna multiply this 4 times, or however many that is. So this is what we have. That's technically what we have. So you could either write out 5, 10, 15, 20 r's, which would be crazy. You could write out 4 r to the 5th powers if you wanted to, or you can know that when you have an exponent raised to another power, they multiply those powers. The powers got multiplied and it became that. So 4 times 5, this is r to the 20th. Just like the last one, we have 2 of all of this. So when I say we have 2 of all of this, that means we're going to have negative 5 times negative 5, or you could look at it as negative 5 squared, which would be 25. And we have 2 v to the 3rd power, which would be v to the 6th power. We have 2 w's, so we have w squared, and we have 2 x to the 4th, which would be x to the 8th. So it's essentially like this 2 gets distributed to each term. Sorry, not each term. Let's just go with term. Each part of this term. And in this term, there is 1 piece, 2 pieces, 3 pieces, 4 pieces. Right? Right. Number 7. Very similar to the last one, where this 4 is going to basically distribute to the exponents. So on top, we would have 4 to the 4th, a to the 24th, b to the 20th, over, well, this 4 still is going to go affect that exponent, and that exponent, and that exponent. Why is it affecting them? Because, again, we have 4 of all of this. So down on the bottom, we have 5 to the 4th power, a to the 8th, b to the 8th. Now, we could simplify that. We could have also simplified back up here. And so, you know what? Let's actually do that just to see how much different the problem would end up being. when you are dividing, this fraction line is dividing. When you're dividing like bases, meaning those are like bases, then you subtract. So it would look like this. It would be a to the 6 minus 2, which is a to the 4th. And that's what's going to be on top, okay? Because 6 minus 2 is positive 4, so it goes right there, okay? And then b to the 5th over b to the 2nd, that's b to the 3rd, because 5 minus 2 is 3. And then, well, what about the 4 and the 5? Now we can't simplify them, right? Because 4 divided by 5 is, I mean, you might as well just leave it as 4/5. It's 0.8. But anyway, so now what we can do is, 4, 5, and all of that is being raised to the 4th power, just like that, right? So you tell me, would you like to simplify this thing or simplify this thing? Either way, we are headed towards the right answer. This is 4 to the 4th, a to the 16th, b to the 12th over 5 to the 4th. I'm going to call that a good answer, okay? Let's go over here, and what we would do is, well, look, there's our 4 to the 4th, there's our 5 to the 4th. 24 minus 8, guess what? 16. 20 minus 8, guess what? 12. We get the same thing, and no, don't say like, oh, it's all real numbers or infinite solutions. No, I was just showing you this was one method for solving it, reducing it. This was a second method, and here we are at the end. Which one did you like better? Do that one. It's totally up to you. Number 8, 6 to the negative 2 power. Well, technically we just kind of saw the introduction of a negative power right there, right? And where was this? Where did it come from? It came from down here. So check this out. That is one reason why this is equal to 1 over 6 squared. Or if you just want to think about it as, hey, negative exponents flip their base, well, then you'd still get this, right? And this equals 1 over 36. Pretty much, if you're not sure when you should go ahead and write the number out like that, if it's pretty knowable, like that's a little annoying to me, but like 6 squared, that's pretty knowable. You know what I mean? And yeah, number 9. So you have a couple of approaches here. You can either go ahead and flip your negative exponents, or you can subtract. And that's, I'm going to do both, right? So first of all, 2 divided by 4 is 1/2, right? If we were to flip, then what we're going to get is b to the 4th on top, a to the 6th, a to the 9th, b to the 9th. And if you're like, well, I wouldn't do it that way. Okay, yeah, I probably wouldn't either. But I'm just showing you that that's how we dealt with that, right? And now we can kind of simplify, make things simpler. So first, let's do the b, because that's b to the 4th and b to the 9th. We have more b's on the bottom. So here's what I'm going to do. I'm going to leave it down there because we don't want to end with negative exponents. And then for a, well, okay, those are down there multiplying each other. You just add them and you get that. So there's our final answer. Let's do the subtraction version. First thing is 2 over 4 is still 1/2, right? But now we have a to the negative 6th minus 9. Well, that would be a to the negative 15th. And we have b to the 4th minus b to the 9th. Well, okay, this is where I would still probably do it the way I did it here and just say, hey, listen, it's really b to the 5th right there. You know what I mean? But if you're like, no, you said you'd subtract. Okay, well, then I'll subtract, and I get b to the negative 5th. And guess what's going to happen when these guys flip? I get 1 over 2a to the 15th, b to the 5th. Same thing, right? Right, using rational exponents. If this freaks you out, don't overthink it too much. We're basically talking about a fraction exponent, okay? And if you're like, wait, what? This is the cube root, which can be rewritten like this. In fact, That one's done. That's how fast this is. And if you don't remember that about this part, then just think, okay, if we have a square root of, let's just go with 2, that's really 2 to the 1/2 power. If we have the cube root of 2, that's really 2 to the 1/3 power. And if you're like, what do you mean remember this stuff? Basically, I'm showing you what would happen if you had a 2 underneath different versions of radicals where the index of the radical was increasing. So see what I mean? If this happened like this, you get the idea? Okay. In fact, I just thought of something. I should have put these on here before I started the video just so that you could have a resource that's kind of all together where, hey, we talked about these things. So this is on Schoology. I asked you to make note cards of these at one point so that you could kind of just review. Oh, hey, when you got a power, when you have the same bases, you add the powers just like that. And here's an example. When you have a power to a power, sometimes they say like this, power of a power, then you multiply the powers. And here's an example. So I'm not going to go over all those, but that was an example. And hey, ta-da, rational exponent. And then, oh, hey, ta-da, more rational exponents, where this one is a little bit more interesting because this 3/5 power right here is only affecting that x, okay? So that's why this 2 right here is still out front, okay? And this, follow the 5, it goes there. Follow the 3, it goes inside. If you're not sure why, we should probably talk because it's been a while since we've done that. Anyway, so now this one. There's a couple ways you could approach it, and I am conflicted on this one because it says write using rational exponents. So I'm going to do exactly what it says, even though I think it could be answered several different ways. And so here we go. The cube root is 1/3 power, right? So we have 1/3 on the very outside, and then this guy is on the inside, right? And then here's where things start to like deviate a little bit. You could do this as 4 to the negative 2/3 power. I mean, and then yes, we have written it as a rational exponent. You could also write it as, well, it's 1/4 squared to the 1/3 power, which would be 1/4 to the 2/3 power. And I mean, yeah, there's a link here too, right? Like that those flip because of it. And then if we were going to get a little bit crazier, the fact that 4 to the 2/3 power, like if we just did 4 to the 2/3 power, that's 16 to the 1/3 power. And that's 2 times 2 times 2 times 2 to the 1/3 power. Well, this 1/3 says we are looking for triplets. And so this guy would actually go out and we'd have 2 times 2 to the 1/3 power, right? And so if this is equal to this, then we could rewrite like that. So here's that answer, 1/2 times 2 to the 1/3 power. That's also technically right. So there's 3 answers here, essentially. I think we should be able to accept all 3 of them, so to speak. And here's the order of which I think is, this is probably the easiest, but you might not choose it because you're thinking about the negative exponent. So I'm going to give this guy I'm going to give him 3 stars. I think he gets 3 stars. So you get 2 stars. And then he gets 1 star because I don't think you're going to do that. And yeah, and if you're like, I'm confused by this right here. I don't usually do my cube roots in exponential form, neither do you. You usually do them in this format, right? Where there's like a cube root, right? So anyway, let's go to number 12, shall we? This is 15 to the 1/2 power. And how much nicer is that one compared to number 11? So much nicer. Evaluate the expression. Okay, so here's where I think I evaluated right here, I think. and this one's evaluate. So anyway, here we go. 27 squared to the 1/3 power, or 27 to the 1/3 power squared. I gotta tell you, this one's gonna be the easy one. He's the winner. The cube root of 27 is 3. So 3 squared is 9. Very easy. But over here, we have 27 squared. Okay, 27 times 27. Let's see, 14, that's 189, 0. 14 with a 1, it's 729. So 729 to the 1/3 power is not that bad, but I could do that one in my head. This one is a little bit more painful for my head. Either way, the answer is 9. But look at these two. Which one is the winner in your mind? I'm a little biased towards this one. Look at it and kind of think about where the road is going to take you, right? This one little step, kind of. This one, that step. And that's where I think you get your answer from, right? So, but that's just maybe me. 14. This, if you're having trouble reading it, if on your paper it's hard to read, this is 1/2, and there's a negative symbol out in front of it. So essentially what's going to happen is we get 1/25 to the 1/2 power, and that's the square root of 25, which is just 5. Now, let's not talk about the plus or minus part. Let's just go with that. And then 15. 81, well, hang on. 81 is really 3 times 27, which is 3 times 9, which is 3 times 3. Notice we're looking for the 1/4 power. Well, the 1/4 power is looking for quadruplets. So there is one set of quadruplets. So the answer pops out 3. 81 to the 1/4 power is 3. Now we're going to be doing some solving. In order for us to solve these, they have to have the same exact base. And obviously right now they do not. But no need to fear. We can make this right side look like the left side by just changing the base. Obviously, you know that 3 squared equals 9. So this was 9, now it's 3 squared. And now, because of what we talked about over here, and because of this, when you raise a power to a power, you multiply those powers. So that's what we're doing here, is that this left side is still just patiently waiting on us. And now the right side is 2 times x, which is 2x. 2 times 3 is 6. And you essentially ignore the bases and now set the exponents equal to each other. That's the only way that those things would truly work out, is if the exponents were equal to each other. So I'm going to subtract x to get x. I'm going to subtract 6 to get -5. X is -5. Just like the last one, that base and that base are not the same. And you might think, well, hang on, this doesn't have an exponent up here, so why do we even care about the bases? How else do you plan on getting an exponent, an x, out of the exponent? I'm not sure how. So what I'm going to do is this part doesn't change. But this 25 is really 5 squared. And oh, look, now they have exponents. So we're going to focus on the exponents. I'm going to subtract 1 and get 1. And then I'm going to flip the signs, and I get x is -1. 18. They sometimes give you a little bit of a hint, like that this is 2, and this is an even number, and it is, hopefully you know, or at least somewhat confident that 16 can be written as a power of 2, and if you're not sure, then you kind of have to experiment till you get there. So how about 2 times 2? Well, that's 4. Times 2, that's 8. Times 2 is 16. So what that means is 1, 2, 3, 4. 2 to the 4th power is 16. Raise that up to the x minus 3 power. And now we distribute that 4 to get 4 to the x minus 12 equals 2 to the x minus 6. So that part on the right doesn't change. And now we're going to ignore the bases because they're the same. And the only way for this to actually be solvable is if the exponents are equal to each other. I'm going to subtract x to get 3x. I'm going to add 12 to get 6. I'm going to divide by 3 to get 2. Oh no, a fraction. No big deal. 1/2, if we were to flip it, would be 2 to the negative 1 power. And that is being raised to the 10x plus 3 power. And on the left side, we have 2 to the 5x plus 2 power. So the bases aren't quite the same. I mean, I guess the bases are the same, but I just haven't distributed that yet. So we're going to get negative 10x minus 3. And let's be honest, we know where this is going. That's a 2. This is 2 to the 5x plus 2. So now those exponents are equal to each other. We're kind of ignoring the bases. 5x plus 2 equals negative 10x minus 3. I'm going to add 10x to get 15x. I'm going to subtract 2 to get negative 5. Divide by 15 to get negative 1/3. This might seem a little trickier, but it's because we need to change both bases. You could probably see it that 4 is really 2 squared. 8 is really 2 cubed. And then can't forget our original exponents, right? Now we're going to distribute and get 2 to the 20x power. That sounds cool. And then we're going to get negative 27x, 2 to the negative 27x minus, let's see, 19, that's 30, but minus 57 power. Okay, so the 2's are basically being ignored now because the exponents are equal to each other, right? So we're going to add, set the exponents equal to each other, right? And we're going to add 27x to get 47x, and that's equal to negative 57. Divide both sides by 47. And I stopped right there because I'm sitting here going, you know what would be really convenient is if you divided by 57 and you would get negative 1. But I checked my math, and here, let's check my math again, shall we? 2 times 10x, well, that's 20x. Okay, that one's pretty straightforward. 2 to the 3rd, so here's what I'm doing. My pencil was hovering just above the screen, not touching it. 2 to the 3rd, that's that. 9 minus 19, okay. 3 times 9 is 27, agreed. 3 times 9 is still 27, and then 27 plus 30 is 57, right? Right. And then they're equal to each other, right? And then we add 27, and we're going to get 47. So as ugly as this is going to appear, we're good, okay? And I think that's just the final answer because we cannot simplify that. And so what I did is I plugged in to Desmos the method where you take this side and you do y equals that, and you take this side and you plug it in as a separate function. You plug in that, and they cross at exactly negative 57 over 47. So this is the answer. Sorry that that's so ugly. I will do my best not to make the future ones so ugly. Next. So this is 4, and this is 1/4. I'm just going to convert this to 4 to the negative 1 power, and this left side is going to stay just the way it is. And now the right side, negative 9x plus 3 is our exponent. Got to distribute that negative 1, And we're going to get 4 to the 3x plus 2 on the left equals 4 to the 9x minus 3 power on the right. We're essentially going to ignore the bases because the exponents are the same. So we get 3x plus 2 equals 9x minus 3. Gonna subtract 9x, because why not? Gonna subtract 2 to get negative 5. And x is 5/6. 5 over 6. So over here, I was not willing to plug in negative 57 over 47 right here. And I didn't want to do it here either, but there's a reason why you would do it. You technically want to do it here because, bases and whatnot. So anyway, I'm willing to plug in 5/6 to just make sure I'm right. So here's what I'm going to do. 3 times 5/6 plus 2. Well, those cancel and I get 5 over 2, which is 2.5 plus 2. That's 4.5. Now I'm going to plug it in here. Because, and if you're like, why didn't you plug it in here? I did, because see, these are the same the whole way down, right? And then this is the most simplified version. So 9 times 5/6 minus 3. Well, so that reduces a little bit. That's 2, that's 3. We're going to get 15 halves minus 3. So this is 7.5 minus 3, which guess what? Is 4.5. That's a really ugly half there. But, so yeah, our answer is officially, and double-checkedly so, 5/6. Graph 6 to the x power. Wow. Check out the scale on this thing. It's going up by hundreds, and this is counting by 1, 2, 3, 4, 5, 6, 7, just like that. So what they're doing here is, yeah, you can go ahead and sneak in a 1 right there if you'd like to, because that would be our initial value. And if you're like, what is the initial value? This is in the form y equals a times b to the x power. Our b is 6, and our a must be 1. It's that invisible 1 out front. That is our initial value. And then now we pretty much just make a table, and we're going to do, okay, so when x is 0, we got 1, which is what that was. When x is 1, we get 6. So again, if this is our scale, 6 is going to be like right here, just barely higher than the other one. I mean, given the scale of things, right? Then we get 2, and that's 36. And if you're like, how's he getting these things? So this is our x. So we'd have 6 to the 0, 6 to the first power, 6 to the second power, 6 to the third power, right? So here, let's go put our 36 on this. So here's 50. So 36 is going to be like maybe right about here-ish, right? And then let's see, 36 times 6. Well, that's 36. That's 18. So this is 216. So 6 to the third power is 216. So here we go. Now, here's 200. So real fast, we're way up here. And I'm pretty sure it goes off the graph from there. Because think about it, it's 216 times 6. I mean, even if you did 200 times 6, that's 1,200. So here is your graph. It's going to be infinitely close to 0. And then it's going to go up like that real fast. There's the graph of f of x equals 6 to the x power. All right, now looks like we're going to be using some calculators, some Desmos. We have a compound interest formula, and then we have, our parent here, and then we have just exponential growth. And you might be looking at this going like, did we ever do that? And the answer is not exactly, because we looked at these and we said like, oh, hey, what if you had a to the 0.5 to the x power? And essentially what we said is, okay, well, so the rate, so 1 plus the rate equals 0.5. And so the rate must equal, in this situation, be negative 0.5. And so we just said, oh, hey, that's decay. and it would end up looking like this. Like, that was kind of what we did. And if you're like, but still, that's a negative. And yeah, check it out. That's a negative too. So if you plug it in here, it would be decay. Yeah, if you plugged in that you were losing 50%, even if you plug it in here, it's decay. If you plugged it in here, it would be growth, and that's not what we have. So anyway, enough talking about that. If these freak you out, let's talk, because we have talked about these at great length. Megan invests $2,500 at an interest rate of 4% compounded quarterly. So let's just stop right there. $2,500 is what she started with. So in our formula right here, P is the number you start with. So 2,500 times 1 plus. Also, another reason why I just did 1 plus is that's 1 plus, okay? And we get it. So anyway, the rate is 4%. That's going to go right here with that little r, and we're going to write it as 0.04. We want to write the decimal, and it's compounded quarterly. That is n equals 4. And check it out, we have an n there and an n there. So that's over 4 raised to the 4th power. And then we're just going to throw in a t. Not because we're just like doing random things, but because t is right there. T is for time. Now, if we had been asked to just write the formula, we could circle this and we'd get out of here. But now we're told how much is the investment worth at the end of 5 years. So what we're going to do is we're going to take this and plug it into Desmos, plug it into a calculator, and make sure to put that the t is 5 at the end. So I'm going to pause it and go do that. So there is my answer. Let's zoom in on this thing. So there was what I typed in, 2,500 times 1 plus 0.04 over 4 to the 4x power. I did x because I'm using Desmos. Yes, that's t, and yes, you could use t. But then I kind of showed you in class how you could do this, and if you missed that, sorry, how you could make this table. So how you make this table, in case you weren't there for that, is you would highlight this. You just click on this, and it would be blue. And then there's like a gear right up here. You click the gear, and then like it would give you the option, and it's got this literally a table-looking button. You tap the table-looking button, and then it would give you this. Notice I just put a box around that. And the reason that I just put a box around that is because I then went and typed 5, and it gave me my answer of $3,050.47.5. So here's how I will count this on the test. It's $3,050, and if you call it 48, I'm good with that, because that's how rounding works, okay? The population of a town is 18,000. That sounds to me like the beginning of a scenario. And then it decreases at a rate of 8% per year. So here's the scenario. You can write y minus 0.08 if you'd like. I think you will do that naturally. I don't think you have to worry about, is it this or is it this? I think you know that it's got to be y1 minus that, because you know that this portion has to be smaller. Sorry, it has to be between 0 and 1 if it's going to be decay. And if things are if they're decreasing, that is decay, right? And then there's our rate, 8%, which is why we did that. Now, notice I didn't write this because it's not compounding interest. It's just decay, all right? And then don't forget your to the x power. And now it says, in about how many years will the population be fewer than 11,000? So that purple part is basically, we want to know, when will this happen? When will 11,000 be bigger than this thing? And now we're just going to take this part, plug it in Desmos. You could actually plug in this entire thing into Desmos. Maybe I'll do that. In fact, before I show you what that looks like on Desmos, I'm going to graph this thing kind of like just normally. And I know that sounds a little strange, but here's the idea. We know it's decay, right? So, and then 18,000 is actually our starting point, right? So it's going to decay like this. It's going to go boom, and then it's going to approach 0 and then level off, right? So they're wanting to know, well, hey, why is 18,000 here? At what point is it below 11,000? So we want to know that dot. And so the reason I'm pointing this out is because if you look at Desmos, I mean, think about this scale, right? This 18,000, 11,000. The scale is going to make it very difficult to read. Now, you can go ahead and graph just this part right here and scroll way up to that and then put your finger right here and you'll get about an answer. And I'm not going to tell you what that answer is just yet. Or you could type this in. And if you type specifically that in, let me show you what you get. You would get something like this. Here's another graph. And it would look like this. 1, 2, 3, 4, 5, 6. And there's going to be like a dotted line about there. And then it's going to shade all over here. So you have to know what you're looking at this point to go, oh, basically at about 6, at about x equals 6, or in our case, about when t equals 6 is when the population will be fewer than 11,000 people. So t is roughly 6, okay? And if you don't believe me, hang on, I'll go get the graph. So here's that first scenario where I said the scale of this will be crazy. So look, I'm scrolled up to 11,000, and then I tried doing this. I'm sitting in my car outside of basketball practice. I was trying to hold this finger down while holding the pencil while doing the screenshot on the iPad, and I get 5.9063. So you could put, yeah, it's 5.9063, except that it said about, so it's still about 6. And then, yes, you'll notice that this one is still there. I'll show you what that one looks like, and it's going to look exactly like this over here, but I want you to see it. So here we go. Hang on. And here is the other one. Like I said, you could type in that whole thing, and it would put it at about 6. See, I did that right here. There's that dashed line. There's its shading, right? And you actually cannot, like, put your finger there and it tell you, because it's like, listen, bro, I gave you an exact answer. And it's, again, going to be like 5.9-ish. Because, look, there's 5, 6, 7, 8, 9, 10. So 5.9, blah, blah, blah. So, again, the answer is 6. And your only other option for, like, really calculating this insanely accurately and forcing Desmos to give you a pretty-looking answer is if you do y equals 11,000 and y equals that. And what will happen is you would get, essentially, you're going to get this again. But look, there's y equals 11,000. Here's this. And it would be now accurate to the 1,000th place, I suppose. So I imagine some of you have definitely stopped listening because you're like, cool, it's 6. Chill out, teacher. But I wanted to go into great detail. So in case you also wanted to go into great detail, you'd be fine. Okay, so there are 4,200 bacteria in a lab dish. The population decreases by 8% every day. 1 minus 0.08 every day. Find the difference, the population. Hang on. Find the difference. I think we're missing a word here. Find the difference in the population on days 4 and 6. Essentially, I think we're just going to do this. We got a t right there. We're going to plug that in the calculator and make t4. See what it looks like? We're going to plug in t is 6 and see what it looks like. And we'll go from there. So just like before, I did the thing. I showed you the button this time. There's the little gear icon. And I'm telling you, if this is highlighted and you hit the gear icon, it's going to give you like 3 choices, and one of them will be a table looking button. Just click the table. It gives you this right away. I didn't mean to like write on there. It gives you this table right away. Okay, so Go away, scribbly writing. And here's what I did after that. I added 4 and I put 6. I didn't really do anything to get that. I just literally hit 4, enter, 6, enter. And then, so that's what happens. At 4 days, the bacteria colony is that big. At 6 days, the bacteria colony is that big. If I really thought they wanted us to actually subtract them, then I would. But I don't think they are. I just think they're saying, hey, find out, give us both of those things. So we did. There we go. Bye. All right, the final competition is a function of the day graph. It's this, negative 4 to the 1/2. I can't talk. It's 4 times 1/2 to the x power. And here's what they want us to do. They want us to graph it. They want us to complete the table. They want us to talk about this stuff. So let's get this table and the graph out of the way as quickly as we can. The initial value is 4. I know that because I am familiar. Oh, you know what? I just screwed up. It's not 4. It's negative 4, right? Why can't I erase that now? Go away. There we go. Negative 4. Right? Because this, I wrote positive 4 here. It's the number out front. How do I know that? A times b to the x, which is our parent function. Parent function a times b to the x is there, okay? And so that's our initial value is negative 4. And then this thing's going to be decaying. But this is, and so here's what decay would normally look like. It would look like this, right? But we don't have that in particular because of this negative, right? It's going to flip it. So don't get too cocky and be like, oh yeah, I got this, is easy. So anyway, when you plug in 0, and it's negative 4 times 1/2 to the 0. That's negative 4 times 1. That's negative 4, which we already said right here. Right. So now let's plug in some other numbers like negative 1. So negative 1, when we do negative 4 to the 1/2 to the negative 1 power, that's negative 4 to the, it's negative 4 times 2 to the first power. That negative exponent is going to flip that. Negative 4 times 2 is negative 8. So at negative 1, it's negative 8. So negative 1, 5, 6, 7, 8, right there, okay? If we were to plug in negative 2, we're going to see something similar. We're going to get negative 4, 1/2 to the negative 2 power. Negative 4 times 2 squared. Negative 4 times 4 is negative 16. So we're off the graph here. That's okay. We don't really have to graph it that way, right? We're going to graph it, but we really don't have to be that pinpoint accurate. Let's plug in x is 1 now. So when x is 1, we get negative 4 times 1/2 to the first power. Hey, we don't have an exponent, so we don't have to flip it now. It's negative 4 times 1/2, which is negative 2. Negative 2. 1, negative 2. And then now, I think you know what's about to happen. When we plug in 2, we're going to get negative 4 times 1/2 squared. That's negative 4 times 1/4. We get negative 1. Negative 1. So at 2, it's negative 1. I hope that you know it's approaching 0, right? So there's our graph. In fact, I'm going to get rid of this part just because it is off the graph, right? There's our graph. The asymptote is y equals 0, okay? It's y equals 0 because it's a horizontal line. Okay, if it was x equals 0, it would be a vertical line. The x-intercept does not exist. We approach 0, we do not intercept 0. We approach 0, we do not intercept the x-axis. The y-intercept is negative 4. It is not just because of that. That's a great start, right? But just remember, it could be moved left, right, up, down. That would impact it. But for us, it is negative 4. In fact, we can go and write it as a coordinate if we want. 0, negative 4. The domain is all real numbers, because as x goes this direction, there are x's infinitely going this direction, right? We will eventually reach negative infinity. Now, yes, it will be way super duper duper way down here, but you will still be going to the left. And then as x approaches infinity, well, we can approach infinity. So that's why it's all real numbers. Now the range is y is less than 0. These guys are very closely related, okay? The asymptote and the range. Also, shout out to Allie, because Allie said, hey, if there's nothing really written outside of here, then it's 0 as our asymptote. So just a reminder on that. I wasn't confident to say that, but she was, and now she gave me the confidence. Thanks, Allie. Next is quadrants. Oh, Easton, where are you at? Easton with the quadrants. It's in quadrants 3 and 4. The end behaviors as x approaches negative infinity, y approaches negative infinity. Because see, it's going down as it goes that direction, right? And as x approaches infinity, y approaches 0. It approaches the asymptote. I don't know if you saw me draw that star there. Those two are related. Transformations. It's flipped. It's flipped and stretched, right? So flipped because it's upside down. Stretched. Actually, no, it's not stretched. I was thinking about the 4. No. Right? Let me go look at it again. Yeah, okay, I guess we could say stretched. Just kidding. Yeah, stretched. This word is a little bit interchangeable for me. If you said, something other than stretched, but I probably would have said stretched. And then, hey, just what else do you know about this function? Well, you guys know a lot of things. It's continuous. Let's see, it's increasing. Let's see, it's actually, I guess we could technically say it's negative, because we never go above the x-axis. Yeah, I guess you could say that. There's perhaps a handful of other things you could say. Oh, it's, I'm thinking like you guys, it's nonlinear, right? Because it's not linear. Did we say it's a function at any pause? I mean, yeah, it's kind of implied in the whole, what else do you know about the function? So, you could have said it's an exponential function. You could have said it's decay. We didn't technically answer that question. Is it growth or decay? It is decay. How come? Because b was 1/2, and if b is between 0 and 1, then it's decay. All right, so I went mega into details on some of these things that you might have been like, bro, that is too much details, and that's maybe a little bit my bad, but hopefully you are feeling like, oh yeah, very much explained, every detail here and there. And if you don't know something still, please talk to me. That's the only way I can help you with exponents and exponential functions, the practice test. See ya.